Okay, let's come to our last presentation. Algorithms for in-place consistent network update. Our presenter Kenda is a distinguished member of technical staff at Nokia Biolabs and a distinguished member of the ACM. His research focuses on simplifying the construction of proofly correct and secure programs. Okay, let's welcome Kenda.
Thank you. So thank you for the introduction. That was just to tell you that I'm not a networking person. I'm from formal methods, but this was a really intriguing problem, and that that sort of spurred me to work on it. So this is joint work with Sugal Ghesi and Krishan Sabnani, who are both from Johns Hopkins University. Okay. So the problem we are looking at is how do we reconfigure a network? And we've already seen some examples of all the problems that can happen when you go from when you try to change configurations. So here we're assuming that you've fixed those problems, that you have the current configuration of the network, you have a validated new configuration, and we're looking at the process of going from the current configuration to the new one. And so what we want to do is, of course, to keep the network operating while this happens. So that creates all sorts of interesting questions to think about. So imagine, just as an analogy, that you have to modify the engine of your car while you continue to drive it, or that you have to change the fly-by-wire software while you continue to fly the plane. So how do we do that? Is this even possible? And what kinds of interesting questions come up with that? So that's what the talk is about. So the first, so if you think about, so let's sort of start by putting down some requirements on the update process itself, right? So the first one is the one we just talked about, that we want the network to keep functioning. Networks are too important. You can't shut them down for half an hour while the configuration is getting changed, right? So we call that update on the fly. The second one is really a memory constraint. So it says that the update should be such that it replaces the routes at each route.
Yes, I'm okay.
It changes them from the current set of routes to the new
I just have this slide.
and this is because
gate 5.
Router memory is
But nobody there.
I'm thinking of
weird.
TCAPs
Too early?
and things like that. So
Sydney.
there's just a limited amount of it. There's not enough to
Flying to
support
Sydney.
both configurations at the same time.
I'll
So you have to replace them.
If my app is wrong.
I mean, they should usually update it
The third
fast.
one is to do with, what do we mean when we say that this process
Yeah, it's still saying gate 5.
5?
and
in the
for
right
that
place.
we just
Oh,
borrow
nobody there.
a really elegant
Just myself. I thought.
from a SIGCOMM'
Oh,
paper,
something
10
wrong.
years ago.
Okay.
And what that says is that, while this change is happening in the network, if you follow the route taken by any packet through the network, then it should belong entirely to the current configuration or entirely to the new one. So it should not mix up configurations. And we'll see that mixing up is bad. And so this makes a lot of sense because the current and the new configurations are well understood. They have been tested. You know what properties these routes have. So you know a lot about each individual configuration. What you don't know is what happens when things get mixed up. Okay. So now it turns out, so the first interesting observation is that it's easy to satisfy any two out of these three properties. So for instance, if you're allowed to shut down the network, then you can just shut it down and restart. So that would be in place, it would be consistent, but it would not be on the fly. Okay. The SIGCOMM' paper gives an algorithm that is on the fly and consistent, but it's not in place because it requires each router to support both configurations during the update, and that makes it impractical. And of course, if you don't care about correctness in this sense, then you can just update routers any way you like, and that would be on the fly and in place, but it will not be consistent. I mean, not in general. So 2 out of 3 is good. It's easy to do. Doing all 3 turns out to be the challenge. And so there's been a lot of work since this paper came out, and you sort of deal with the problem in different ways. You weaken consistency. You allow a little bit of extra memory at each router. So there's lots of ways of doing it, but nobody's done all 3. And that's what we do. So we give an algorithm that updates configurations with all 3 properties at once. But, and there is a but, our algorithm may drop packets, and it does so only when forwarding the packet or processing the packet would cause it to lose this consistency property. So experimentally, we found that packet drops reduce throughput by 10 to 20%. That's a big number, but it's less worse than what we had thought. And we show that by doing some lightweight network analysis and analysis of the updates, you can actually either limit these packet drops or avoid them completely in some situations. And this is very much an active area for further work. But the most interesting thing to me as a formal methods person is that we can prove that packet drops are unavoidable. So if you have any algorithm that meets these three requirements, then there are scenarios in which it will drop packets. So you can't get that number down to 0. I mean, of course, we want it to be less than 10 or 20%, but you cannot always get it down to 0. Okay. So that's kind of a summary of this entire work, the highlights of the work. And one of the other interesting aspects about this is that we build on classic distributed systems construction, which is called the Chandy-Lamport snapshot. And so this is a really nice example of taking notions from a different field and then applying them to a very practical problem in networking. So what I want to do next is to really just give you a flavor of the problem to show you why it's challenging and fascinating both, and then to give you the key insights behind the solution. So I'm going to simplify, I'm going to drop a bunch of details. There's things I won't talk about, but all of that is in the paper. Okay, so let's go. So the problem turns out to be that of mixed configurations, as we've just thought about. So think about this as a network. The circles are routers. I'm going to color code configurations. So the current configurations is going to be red. The new configuration is going to be green. Right? So you want to move this network from all red to all green. That's the idea. But of course, you can't do this all at once. So you have to do this piecewise. And so you change routers one by one, and you can see that there's why there is a problem. Because unless you control the flow of packets, you're going to get routes that look like this. So packets pass through a router with an old config or the current configuration, move to the new one, get deflected back to an old, move back to the new, and things like that. And you have no idea what this route, what properties this kind of route has, because it's something completely new. Okay. So a very concrete and simple example of this is this circular network. So there's 4 nodes, north, south, east, west. The blue arrows represent the actual physical links, the little dots represent packets. So you can imagine configuring this in 2 different ways. So in the red configuration, all packets that go in are going to exit through the north node. The green configuration is symmetric, but all packets exit through the south node. Right? So the dashed arrows represent the actual forwarding decisions. Okay, now let's see what happens. So you start with this red configuration. You have this packet over here. It moves along. It's still in its red configuration, and now it's waiting to be processed by the north node. Now at this point, let's say you update the north node. Okay? So now it's pointing to the west, right? And if you don't control, if you don't put any sort of controls on this process, if you decide to, if the north node processes this packet, it's going to end up at this edge, back at the west node. So what you've just done is to create a routing loop. And this loop does not exist in either of these 2 configurations. It's an artifact of this update process. So, I mean, you might say, well, this loop will eventually go away because, once you finish updating all the routers, they're going to be in the green configuration, so it's all good. But, so in that sense, yes, that's true. So in that sense, a routing loop is kind of a benign problem. But you can easily construct scenarios where, during the update, packets can completely bypass firewalls. They can, they can go to the wrong sections of the network. They can sort of break all sorts of security policies. I mean, these are easy exercises. Think of this as a homework exercise to try out when you get back. So there's all sorts of things that could go wrong. And even though the update does eventually complete, this creates a window of opportunity for people to hack the network. And so we want to shut down all of these windows. Okay. So I'm going to go now to start moving towards the distributed systems view of things. And so I'm going to take that same computation and view it in a different way through this thing called the space-time diagram. This is a very common way of seeing computations in distributed computing. So all I've done is to have a timeline for each node. So I'm going to represent events as they occur on the node. And since the update is in place, so if you look at the west node, the timeline, all of the initial events are going to be in the current configuration, that's red. Then there's this black bar that represents the update point, and everything else is in green. Right? So let's see what happens. I'm just going to replay the same computation. So, before I do that, if you connect up all of these update points, right? Now that represents something that's called a cut of the computation. So it's basically a global network state. And you would like to imagine that the entire network updates at this point, at this global state. Right? So now let's see what happens with this computation. So you start moving this packet along. This is the packet going around the ring. And so everything is still to the left of the cut, which is good. But now when you send this packet to the north node and it gets processed, it's going to cross the cut from left to right. Okay? Now when the north node sends the packet back to the west, closing the loop, it's going to cross the cut again, but this time from right to left. Okay? So this sort of suggests that these crossings have something to do with the routing loop and the problem. Right? And indeed they do. So the network state that's defined by this cut is causally just impossible, because the receive of the green packet happens to the left of the cut, but that packet hasn't been sent yet because that's to the right of the cut. Okay? So this is just an impossibility. And secondly, the state is non-quiescent in the sense that the red packet is in flight across the update. That's the original crossing that we saw. Okay? So now imagine that you had a cut where everything was causally correct and the cut was quiescent. That would mean that the cut was consistent, and that all of the red actions were to the left of the cut, all the green actions were to the right of the cut. So this would establish consistency. So we need this mechanism to ensure that every update cut is correct and causally correct and quiescent. And so this is where we use the Chandy-Lamport snapshot algorithm. This is a really amazing construction. If you haven't seen it yet, I strongly recommend that you read the paper. You'll enjoy it. Okay. So the update algorithm, the way it works is that it has a special control packet called a marker. And as the marker moves through the network, it updates nodes. Okay? But it also has another function. It separates out the green from the red. And so it does so by following some very simple rules. So everything starts in the red state. As the packet moves along, the update controller is going to send markers to some initial set of nodes to get them updated. And so that's that little triangle. So now the interesting thing about this algorithm, the crucial part, is on receiving a marker, a node does three things. It updates its rules, it flags the input channel, and then it forwards that marker out onto all of its outgoing channels. Right? That's sort of flooding through the network. And so this is what's happening. And as the marker moves along, behind it, there are green packets that are just getting processed by the new configuration. But what about that little red packet over there? So we can't accept it because that would break consistency. So it has to be dropped. Okay? And so that's the last rule, and that's the end of the algorithm. Okay? So you can see that it's a very simple algorithm to implement. And it has this correctness property that every every computation that you get with this algorithm is equivalent to one where the update cut has those two nice properties of being causally correct and quiescent. Okay? And the impossibility result basically says that you're going to end up in this dilemma where regardless of what algorithm you have, there are scenarios where you'll end up in a dilemma where you have to, where accepting the packet would violate consistency, so you have to drop it. Okay, so now just look at a couple of results, just one result here on the AT&T rocket fill topology. So this line represents the throughput without an update. And you can start the update at any set of nodes. It's still going to work. So the natural place to start it is at the edge of the network. And so there we see a throughput loss of about 15%. Okay. If you start it at some other nodes that are deeper in the network, then you get a much higher throughput loss. So, and this is something that we observed in all of our experiments. So starting at the edge seems to be the right thing to do. This is the update time for the entire network. So it turns out theoretically it updates in time proportional to the network diameter, because that's the time it takes to propagate the markers through the network. And it turns out that it's not very different depending on how you choose the nodes. Okay. So let me summarize. So we have this really simple method. The implementation just has a almost trivial state machine. It's about 50 lines of P4. So what I didn't get into is that it also supports stateful components naturally. So you don't have to change the algorithm. You can handle stateful firewalls, for instance. Interestingly, it's oblivious to the actual update. So you don't need to analyze the update to figure out whether the algorithm should run or not. Right? It's going to update no matter what you ask it to do. And it's easy to make it resilient to temporary node or link failures. So all of this is in the paper. And we proved this impossibility theorem that says that packet drops are unavoidable for any algorithm with these properties. And so now we do have this 10 to 20% in the experiments, and so we have thinking about various ways of playing around with network analysis and update analysis to try to control the algorithm a little more and to see if we can get that reduced. But that's ongoing work. Okay. And finally, for somebody, like I said, who comes from formal methods, this was really a fun thing to work on. This is taking an algorithm and concept I had long admired, the Chandy-Lamport snapshot, and then finding a very practical use for it in networking. So thank you, and happy to take questions.
Thanks. That really a lovely talk. Appreciate it. I may have missed it, but how does the updated node know to drop the? How do you get it to drop the packet? Okay. You're not changing the switch or anything, are you?
No, but we have a little update shell, if you like, that is managing these markers. So the markers, you can think of it as there's the actual rules that are updating, and then around it is a little shell that intercepts the markers and decides what to do with them. It also intercepts the packet and decides to drop
once
them.
It sees the market, it just drops everything until it's updated?
Once it gets updated, it drops everything on an input channel until it sees the marker come in.
Thank you.
Yeah.
Hey, thanks. Really cool talk. So pick two, but that I guess is on an arbitrary network. Mm-hmm. If you were able to design the network or specify the types of changes, could you get all three?
Yeah, that's a really interesting question. So one of the things we've shown in the paper is that, this is not a practical thing, but it's an interesting concept nonetheless, is that if your network doesn't have cycles, then you can update it without any packet loss.
Okay.
So now, could you do some further analysis, some sort of lightweight analysis of the update, and use that to further reduce the packet loss? So I think this was not exactly your question, but but there's sort of connections there in the sense that you want to do some analysis of the network and say that networks with certain properties, you can actually update them more efficiently.
So I'm quite interested in how you use design patterns to make networks do what you want them to do, and that's kind of where the...
Yeah, I think that would be great, but right. So I think I heard some people, there was a talk earlier saying that networks are evolved but not designed. So I don't know if that is true. This is something that you guys know better than I do.
I think it's a bit of a mix. Like engineers would like to design everything, but don't always get a complete carte blanche. Yeah, so I think that's a really interesting question. So if you could sort of pick the network topology, then could you get all three properties? Yeah. Cool. Thanks.
Yeah.
I have two questions. First is a simple one. How does current network conduct those updates? Welcome for industry people
This
to
is-
answer, maybe.
Yeah, this is actually not a simple question because I have no idea. So I tried, when we wrote this paper, we tried to find, literature on how network updates are done. And the only thing, I mean, you guys are the experts, you should know, maybe somebody else can answer this question. But the one thing I do know is that, the service providers, like the telecom providers, like they know that they have less traffic during nighttime, for instance. So they kind of shut down portions of the network and then update and then, switch traffic back during the daytime. So this is what they do, but I actually don't know how, other kinds of networks are updated. So.
Okay, thank you.
Mhm.
The second question is, I don't know your proof of the drop is necessary.
Yeah.
So I'm just wondering if we can delay packets instead of drop it.
You can delay, yeah, but you can delay only up to, basically if you delay packets, then you're delaying the entire update process from completing. So there's kind of a trade-off there. So, you would have to delay, I think these are two different things. So you can, in our algorithm, you can actually set the delays. So you can delay some packets, delay the updates from happening so that, more of these red packets can be processed, right? So you don't have to drop them, you can just process them because the node has not updated yet, right?
Yeah.
But you can't delay forever because eventually the node
Yes.
has to update. And then you end up in this situation. I don't think there is a way to avoid it.
Yeah, but it's better than the entire network down, right?
Yes,
Okay.
yes, it's definitely better than having the entire network down.
Thank you.
Yeah. Okay. Yeah. Okay.
Yeah, we are already running out of time, and but let's thank all of our speakers again.